Afternoon. This class will be on the molecular electronic structures and modeling of molecules for nanoelectronics. So during this class we try to understand how the molecules can be described, how the molecular orbitals will be can be derived starting from the single atoms orbital analysis. So this class is organized on a brief introduction. After that we will discuss on the electronic structure of atoms. After that we will try to reconsider some basic aspect of wave equation, Schrödinger equation, to find the atomic orbitals. After that we try to understand how we can define and derive the molecular orbital starting from the atomic ones. And at the end we try to define a scheme for electronic application of molecules in terms of energy levels and electron interaction with molecules. Okay, so as you know, molecular electronic structure are built up by few atoms, and the interaction of the electrons with the atoms arrangement define electronic properties. So in traditional electronics we have similar problems, but you know that in material for electronics generally we have regular structures, we have lattice where the electron can be described by using many tools developed for electronics, like energy band energy diagram and so on. In traditional electronics, dimension till now are larger than in molecules. Molecule dimension are few nanometers, and probably the same dimension will be reached by electronic devices, traditional electronic devices, by 1 decade, 10 years. But there are differences between electronics in semiconductor and electronics in molecules, because even if we have a very, very small structure done by semiconductor, generally that structure are regular. So we have a repetition of the same structure, and some properties can be derived from this kind of regularity. In molecules, the problem is completely different, because as we know, the properties of molecules depend on the internal structure, and the internal structure is defined in a more free way. So we have to study in detail how atoms are organized and how the molecular orbitals are inside the molecules. Without this information, it is impossible to understand the current and the electrical behavior of molecular devices. So, in molecular electron devices, we will start studies by a review of the atomic orbitals and how organic compounds will modify atomic orbital to allow electronic properties in devices. So, in this very brief review, you probably remember that when you describe atomic orbitals, you can consider a very simple model where the positive nucleus and the negative electrons are bound by electrostatic force, and the potential energy is defined by very simple equation that you have there, where the energy is a function of the charges. If we have just one proton and one electron, q square over 4 p epsilon 0 and radius, in other words, the distance between electrons and the nucleus. So this is a very, very simple model for the atoms. But you know that the electrons can be described only in terms of wave function. Wave function can be evaluated starting from Schrödinger equation. Schrödinger equation is a well-known equation that you have studied, and you know that Schrödinger equation generally is solved by separating the dependency of the wave function from the energy and the time. So generally we use separate variables. That means that the wave function can be described as a product of ft dot psi function of the point of x, in this case, if we have a one-dimensional equation. So if we try to substitute in the general form of the Schrödinger equation a separate variable form, we can obtain the last equation in the slide, and that means that we have a separation constant called energy, the total energy of the electron. So the Schrödinger equation can be rewritten as a system where we have one equation only depending on time, the first one, and the second one where the equation is defined only as function of the coordinate of the electron. In this case is one-dimensional 1 by x. So the last one equation is the basic equation to define eigenfunction and eigenvalues for electrons in a system. So probably you know that the Schrödinger equation can be seen as a system where you have for definite energy solution you have an equation that is the minus potential energy so this is very studied equation and can be seen like a system where you have this equation, but you have different, the system is described by the potential function, the function of the potential for the electron in that system. So starting from the description of the system, for instance, I don't know, in semiconductor is well known the potential like this. So the electron can be bound to this system because if we imagine that the total energy of the electron will be less than the height of this structure, the wave function equation, the Schrödinger equation, will produce two things. In other words, eigenvalue, the total energy of the electron, W or other, and the eigenfunction. So probably we have the ground state and the other one. So each eigenvalue and eigenfunction will define a probability that the electron will be inside this stratum. You know that the ground state will be like this, with energy W0. The second one probably will be like this. You know also that the wave function C0, 1, and so on can be associated to a density of probability just evaluating the square, modulus square of the function. So you know that this quantity will be the probability to find the electron in a place. In this case, the energy, the total energy of the electron is perfectly known. So for this reason, it's called definite solution, definite energy solution. If the energy is known, we can also know the waveform, and from the waveform we can define the probability. So in the case of a very simple structure, the solution of this equation is really easy. So we can solve in many interesting cases. But the problem is atoms and molecules have a potential function and a structure more complex than the cases like that. So probably we have to apply the Schrödinger equation to more complex system. The general form that you generally see for the Schrödinger equation is this one. So you have a Hamiltonian operator that describes completely the system. So in this case is that expression. If we consider a simple atoms with one positive charge and one negative charge, we can replace the quantity U with the previous one. So the Hamiltonian for a simple atom is this one. So the solution of this equation is not so easy because it requires many mathematics and not so. But now we can understand why it's relevant for us to consider, to reconsider this solution. Because orbitals of atoms will be used as basic blocks to define molecular orbital. So the effort required to solve a Schrödinger equation and to find the atoms orbital, atomic orbitals, is the first step to define a basis set and to evaluate or to estimate in a good way the molecular orbitals in more complex structures. So this first step requires the solution of Schrödinger equation for this case. So the solution generally is done by using spheric coordinates. So in spheric coordinates we have three variables that are radius, r, and the two angles, theta and phi. So we can obviously rewrite the equation by substituting these coordinates. The solution by mathematical point of view, as I said, is not so easy. Is a good exercise and is a good achievement for the last century physics and mathematics. So probably you know that the general solution for that equation is a very complex function, but this function, if you try to consider with more care, depend only on three numbers, three quantum numbers. These numbers are n, principal number. This number is integer, 1, 2, 3, and so. L, angular momentum number. This number is constrained as value starting from 0 to n minus 1. And the last number is magnetic number, is ML. And this number is, the range is minus L to plus L. So these three numbers, from a mathematical point of view, define all the functions that are solution of the wave equation, Schrödinger equation, with electrostatic potential. So this term in the equation, the term in the equation are briefly explained here, but is not the aim of this course to do this kind of calculation. You can find this kind of equation, kind of polynomials in quantum mechanics textbooks. But for our purposes, it is relevant to reconsider the result. For instance, the hydrogen atom, hydrogen atom has just one electron and one proton, and the function can be defined mathematically as psi with the 3 atomic number 1, 0, 0. If you try to substitute in the general expression for the waveform these 3 numbers, you can get that mathematical function. That function describes the wave, the waveform, the wave function for the electron in the system. So we can try to draw the density of probability associated with this wave function. So we can try to draw it, and you have just approximately sketch there. And you see that the probability to find the electrons around the proton is this kind of curve. So you can derive this curve, you can define and find the maximum, and the maximums will be the radius for hydrogen atom. This is a very simple procedure, but also effective, because the number that you can find in this way is exactly the same that you can measure experimentally. This had been a very, very big success for the quantum mechanics in last century. And also for us is a good starting point. That means that this orbital, this function, can be used to define orbital for the hydrogen atom. So it is also clear, if you try to draw a figure, a surface, with the same probability, you can derive the shape of the orbital. In the case of hydrogen, the shape of the orbital, in other words, the surface where the probability has a fixed value or a determined value, is spheric. It's clear that for single atoms, you can define orbitals and you can evaluate energy. So you know that for every kind of orbital, S, P, D, F, if you try to consider different principal quantum numbers n, you can find the different energy of the electrons when are in that orbital. So for hydrogen, the electron will be in orbital S, and their energy will be this one, and so on. For more complex atoms, you have more electrons in different energy levels. For instance, for carbon, you have 2 electrons in first energetic level, 2 in 2s2, and 2 in p orbital. So this is a good result, because you are able to understand which are the energy of the electrons inside atoms, and you can know also how these electrons move around the protons in the orbitals. So, as I said before, for s orbitals, you have spheric orbitals. When you consider p orbital, you have two lobes like that, where the density of probability for electrons is defined. But now we are interested to molecules. Molecules are systems where atoms are bound each other. So for us, it's interesting to understand how the result obtained for single atom can be used to define molecular orbitals. You know that in solid materials, the properties, the chemical properties and the electrical properties are function of the different internal structure and different kind of bound. So you know that when the atoms inside the material are bound mainly by electrostatic force, you have ions, and so the bound are due to the attraction and repulsion between ions with different signs. You have a covalent crystal, covalent material, metallic, and so on. Probably, now we are not interested to consider materials, but now we are interested to understand covalent bonds. And the simplest example for covalent bonds is hydrogen molecule, H2. So when you try to put two hydrogen atoms in a position where the orbital interacts each other, some things happen. From the quantum mechanical point of view, you know that when the two atoms are enough separated, these two systems are completely independent. That means that for these two hydrogen atoms, you have the same wave function, the same energy for electrons. But when the distance is reduced, these two orbitals interact, and the system, from the quantum mechanics point of view, is just one. That means that we have to modify the orbitals, the atom orbitals, to define molecular orbitals, because probably the electrons inside the system have a different energy with respect to isolated atoms. So now we can try to understand how we can study this kind of interaction. Here we have the solution, because you know that this molecule, H2 molecule, is stable, and probably that means that the electrons are shared by the two atoms in a condition where the total energy is at the minimum. But now we have to understand how we can evaluate that kind of orbital and the total energy and the energy of the electron in this molecule. So the idea is very simple, and this idea is used by all molecular simulators. The idea is to use the LCAO, in other words, linear combination of atomic orbital algorithm. In other words, we can produce molecular orbitals just doing the linear combination of the atomic orbitals. In other words, we can imagine that each atom has one wave function, and when the atoms are separated, these two wave functions are the same. We can call to distinguish them phi A and phi B for the two hydrogen atoms. So we can define the wave function for the hydrogen molecule by combining the two atom wave function. So we can say that we have a symmetrical wave function for the hydrogen molecule, CS, symmetrical form, where we had the two atomic wave function, and the other one can be defined as difference between phi A and phi B. And we can call this wave function C asymmetrical, AS. So now we can try to draw this kind of solution. It's very simple because, as I said, the orbital for atomic had been exactly derived from Schrödinger equation, from wave function equation. So we know the mathematical expression for orbital S for hydrogen, A, and wave function orbital S for atom B. Now we can produce the molecular orbital, and we can do that in this way. So in this figure, you have on the top, you have the symmetrical form. So you had done the sum of the two wave function, phi A plus phi B. And the second one is the difference. This figure is not completely honest, because you know that the wave function generally are complex function. And in the practical, you cannot draw in this way a complex function. Probably this can be an idea. What we can do is to draw the modulus, the square modulus of this quantity, because associated with this function, the square modulus of this function, we can evaluate the probability to find electron. So probably I can try to draw this probability. I can try to define, this is x-axis, it's just one-dimensional. Sorry, this is a forbidden color. I have to drop it. So, hydrogen A, positive charge, B, positive charge. Now I try to define square modulus of that function. Probably for the symmetrical form, we have a curve like this. So this can be square modulus of symmetrical form obtained by summing by the sum of the two wave function. And here I can do the same for the asymmetrical form, but what we can get is probably a form like this. Here is 0, and probably this one. So the second one is square modulus of the asymmetrical form of the molecular orbital. So this is a density of probability. And what we can discover is a very simple thing. The electrons in the H2 molecule can be found with quite high probability between the two atoms for the symmetrical form. And for the asymmetrical form, we discover that the probability to find electrons in the middle between the two atoms is 0. The other thing is that if you try to reduce again the distance between the two atoms, the probability is always 0. But it's clear that the two atoms, probably, and the electrons are not in a stable condition from the energetic point of view. In other words, if you try to evaluate the energy for symmetrical form, the energy for the system is at the minimum when you consider the electron in the symmetrical waveform. And the energy in the system is higher when you try to put electrons in the second molecular orbital or asymmetrical orbital. What we can say is, and this is a very common way to understand what I said, is when you consider a hydrogen molecule, we have the orbital of the atoms on the left. So this is the energy for the atomic orbitals for separated hydrogen. When you produce a molecule, we have two different molecular orbitals with separated energy, and we understand that the energy associated with symmetrical form is the bonding molecular orbitals. Means that the stable form for the hydrogen molecule is this one. The two electrons of the two original atoms will occupy the bonding levels. In other words, this is the sigma orbital, the sigma type orbital. The antibond or bonding orbital. The asymmetrical is associated with this one energy and is called antibonding. In other words, this is not a stable condition for this kind of molecule. And you know that, and you see that the energy is much higher. So the idea is to define molecular orbital starting from atomic 1. So if you have an idea of the atomic atomic orbital, probably we are able, by using linear combination of this atomic orbital, we are able to define the energy level and molecular structure for that orbital. Probably for us it's not so difficult to understand the shape of the orbital for sigma bonds. Because probably from this probability, this is just one-dimensional, probably we can understand that the form of the orbital should be probably like this. For me it's not so easy to define, but probably we can associate to this probability this molecular orbital for the bonding level, and so on. This is a general idea, I said, and is a technique used in many simulators to evaluate molecular orbitals. For us it's important to know just a little better how organic compounds are bound. But you know that carbon is very interesting atoms, because you know that carbon can be in the ground state, and you know that in the ground state is you know that for carbon, 6 electrons, you have a electronic configuration, very easy, because you have 2 electrons for the 1s orbital, 2 electrons for 2s orbital, and generally you can write 2p2. But you know that if you try to look with more care to p orbital, you know that the orbital could be represented in this way. So this is 1s, 2s, 2px, 2py, 2pz. So in the ground state, the electrons are 1 up, 1 down, spin up, spin down here. And you know that you have 1 and 2. So this is the carbon in the ground state. But carbon can produce hybridized orbitals. Hybridized orbitals are produced when the carbon is in excited form. So when the carbon is in excited form, one electron from 2s orbital will move here. So the condition is this one. The inner layer is unchanged, but here we have 1, 2, 3, 4 unpaired electrons, respectively in the orbital 2s, 2py, 2pz. But what happens is that the orbitals, when the carbon is excited, change, because this interaction, there is an interaction between 2s orbital and 2p1s, producing new orbitals called hybridized orbitals. What is an hybridized orbitals is not different from the hydrogen molecule. In other words, you have to combine 2s and 2p orbital, producing new shapes for hybridized orbital. But this time is done inside the same atom, not between 2 different atoms like in the hydrogen molecule. So what is an hybridized orbital can be understood with this picture. So this is a typical hybridized animal. So in the same way, s orbital and p orbital will produce new shape in this way. So you know that hybridized orbital can be sp, sp2, sp3, depend on the quantity of the p orbital involved in the hybridization. So here we see that the three p orbitals interact with the 2s orbital when carbon is excited. So for sp orbital, what happens is s disappears, interacts with the first p orbital, and will produce 2sp orbital. And 2p orbital, original one, are unchanged. So the carbon structure for the this form of excited carbon is this one. So you have the 2 lobes obtained by sp orbital. Sp orbital are can be derived in the same way that we did with hydrogen. So you can do a combination of wave function for the spheric orbital 2s with the orbital 2px. So you can add and subtract this lobe and this sphere. So you can obtain two orbitals with this shape in the opposite direction. So these two orbitals, these two shapes, are x-oriented in this case, and the other two, py and pz, are this one and this one. So you have a structure where the angles between sp orbital and the p orbitals are defined by the geometry of the atoms, okay, of the orbitals. So we can continue, and obvious that this kind of interaction can be, this time, between 2s orbital and 2p orbitals. In this case, we will produce 3 sp2 orbital, this one, and just one p orbital will be unchanged. So when you consider the excited carbon orbital, you have a trigonal structure where you have 1, 2, 3 sp2 lobes, main lobes, and this p orbital, pz, is in the middle. Again, you have angle defined by the orbital structure. So we can continue, and the last one is sp3 orbital. In this case, 2s and the 3p 2p interact, will form 4 sp3 orbitals, and the structure will be tetrahedral. So we have 4 lobes adjusted in this way. So these are 3 possible forms for excited carbon, but the excited form are useful to produce many organic compounds, because when you try to understand how molecular orbitals interact in organic compound, many times you have to consider one among these 3 excited forms to understand the resulting molecular orbital. So we can say that when the orbitals are hybridized, are ready to bond. This is what this T-shirt say, and it's exactly the same for carbon. So, first example, if we use excited carbon in sp3, we can produce, by bonding 3 hydrogen atoms with the 3 sp3 orbital, with the 4 sp3 orbitals, we can produce methane, CH4. So we can understand this structure because, as you can see, this is the original sp3 form for excited carbon, and here we have sigma bond. Sigma bond is exactly what we discover for H2 molecule, because again we have like a covalent bond between hydrogen and sp, one of the 4 sp3 orbital. So probably the maximum density of the electrons for hydrogen and sp3 will be in this region, in this region, in this region, and the structure is this one. So we can understand that the methane can be explained in terms of hybridized form of the carbon plus 3 sigma bonds, 4 sigma bonds with hydrogen atoms. So we can continue this simple idea, and we can produce, for instance, a very important, my colleagues will explain you the benzene ring, and the benzene rings is very common in many organic compounds used in molecular electronics. We can explain quite well as a benzene ring can be formed starting from 6 carbon atoms and 6 hydrogen atoms. Since you know that benzene is a ring with 6 atoms, and you can understand that this ring is formed by carbon excited in the form sp2. If you remember, in the form sp2, we have one unchanged p orbital, pz, that is in this direction. But the other one, 3 sp2 orbital, are on the same plane. So 1, 2, 3, and can lay on the same plane. Otherwise, the pz orbital is in the orthogonal direction. So we can understand that we use 6 carbon atoms. We can bound by means of sigma bonds the orbitals on the plane of the ring, and probably the pz orbital will be in change and probably will not interact with other sp orbital. So the idea is really simple. The structure, the planar structure of the ring is due to the sigma bond between sp2 orbitals, forming a ring. So all carbon can produce bonds with other carbon by sharing, like in hydrogen molecule, by sharing the 2 sp2 orbital. The 6 pz orbital are unchanged and are in this direction. This condition is well known in organic chemistry, because you know that this pz orbital will be forced to interact each other, because the length of this bond put the pz orbital so near each other that this pz orbital will interact each other. This kind of condition is called conjugated. This is a typical conjugated structure, because this pz orbital will interact each other, and you know that the resulting orbital can be represented like this ring, this strange ring, 2 rings, and are called p orbitals. P orbitals are very important in molecular electronics because, as I said, many interesting compounds with a specific electronic property are based on this idea, or are based on conjugated compounds. In other words, I tried to summarize some relevant concept, some relevant idea for our application. In conjugated molecules, orbital pz strongly overlap. This means that our analysis technique can consider independently this orbital. In other words, even if the system is quite complex, we can do some simplification, because we can apply linear combination of atomic orbital separately with pz orbital. We have not to reconsider all orbitals together, 1s, 2s2, and so on, but we can focus only on the molecular orbital deriving from interaction among the pz. So this is a good idea, is a good method to reduce the complexity, the computational complexity, to obtain molecular orbital in conjugated molecules. The other thing is, when you consider a p orbital, this ring, is quite easy to understand that electrons in that orbital can move quite freely inside that orbital, because the energy of electron is the same in any place of that ring. So this is a hint to us to understand that probably conjugated molecules have good opportunity, good basis for electronic transport. Another important thing is generally these rings are larger than molecule. So when you put a different ring like this in a molecule, probably this ring can interact each other. So it's possible for electron to move from one ring to another. So you can define molecular wires where electron can move from one p orbital to another one if you are able to synthesize molecule with many rings inside. Now we can try to summarize some ideas. It's clear that what I said can be understood when the structures are simple, but molecules used in molecular electronics in many cases have a very complex structure, so it's difficult to evaluate with a simple calculation the structure of molecular orbital. We can have idea of the general shape. We can understand how orbital can be derived from the chemical structure, but it's very difficult to evaluate the energy levels associated to the molecular orbitals. In general, in molecular electronics, we use some reference level. The first one is the HOMO, H-O-M-O, that is the highest occupied molecular orbital. At this level can be associated to the valence band in semiconductor. So is a level generally occupied when the molecule is in the ground state. Corresponding to the conduction band and conduction level in semiconductor, we define LUMO, LUMO level is the first, the lowest, not unoccupied molecular orbital. Generally, molecule can be described by these two levels. And these two levels generally are separated by some electron volt, and the HLG, the distance between LUMO and HOMO levels, has a correspondence with the energy gap in the semiconductor. So, for us it's difficult to evaluate this value just by applying ideas similar to that I did just before on benzene ring and other simple conjugated molecules. But we can use simulator. Simulator will evaluate energy level, molecular orbitals in a manner quite similar to what I did. So The idea is to use a basis set. The basis set is a set of functions, and generally these functions are mathematical functions that describe atomic orbitals, S, P, and so on. The simulator tries to optimize the structure of molecular orbital by applying the linear combination. In other words, if C is the wave function for the electron in the molecule, we can define this wave function by optimizing this sum. So we have some coefficient that we optimize and some function, gamma function, that are the basis set. So the simulator will produce molecular orbital. Each molecular orbital has an energy. So we can get for each compounds a structure like this. So it's quite clear that starting from a description of the molecules in terms of atoms and their position in the space, simulator can produce molecular orbitals and can associate to each orbital an energy. So it's quite clear that in a ground state, the molecule have all the lowest level occupied, and starting from LUMO plus 1 and so on, are free and can be obviously occupied when the molecule is in excited form. This is the basic idea. Starting from this, we will try to understand how a molecule can interact with electrons and how electron can move from metal, from interfaces to molecule, and from molecule to electrodes. But this will be the topic of the next class. Thank you. Any question?